All right, we are now being recorded. I would like to introduce our speaker today, Dr. Brian Dzwonkowski. I really hope I'm pronouncing that correctly, Brian.
That's pretty
Brian
good.
Is an assistant.
That's pretty good.
Awesome. Great. Brian is an assistant professor in the Department of Marine Sciences at the University of South Alabama, where he has been a faculty member since 2014. Brian's research interests lie in coastal physical oceanography, i.e. things related to the structure and flow of water, such as currents, tides, and stratification, as well as how physical processes impact biogeochemical cycling and ecosystem function. He spends much of his time trying to understand the dynamics of Mobile Bay and the Mississippi Bight. So Brian, I am going to turn the presentation over to you now. Just one moment, please.
Sure.
And I'm making you a presenter now.
All right. Thank you for that introduction. Yeah, so show my screen. I'm going to do that. And let's just make sure I have everything in order here. So sharing, let's see, screen. And I'm going to do the entire screen. And then, so let's go to presentation mode. So I'm assuming everyone can see my screen. This worked when we tested it out on Tuesday. Perfect. Okay. So yeah. So my name is Brian Dzwonkowski. I'm a researcher at Dolphin Island Sea Lab and a assistant professor at the University of South Alabama. And so this is today's talk is going to be about a project that was funded to try to improve access to a historical data set that we've been collecting at this offshore site in the Mississippi Bight, right? And so the title is The Little Buoy That Could, because this station has been out there plugging away despite limited funding opportunities and constantly being tested by the environment. This buoy just keeps on chugging away. And I've also been reading a lot of children's books lately. I have a 3-year-old, and I've been getting lots of quality time thanks to COVID-19. And so I figured go with that mantra. And so that's why this talk is called The Little Buoy That Could. And so hopefully I will convince you by the end of this talk that the efforts that we've been putting into this buoy have been and are paying dividend and will continue to pay dividends for the science community, for the management community, and hopefully the general public. And so this project was put together by myself and Renee Collini. And so I just want to acknowledge, and then we've had later on in the talk, there's some applications of this data that brings in some of these other co-authors that are listed on this presentation. And so we've had a lot of hands playing around in this project, and I just want to thank them all. And so getting into that, let's talk a little bit about why we needed to conduct this project, right? And so environmental conditions are critical to understanding changes and dynamics of coastal ecosystems. Getting accurate, robust, and accessible environmental data promotes improved management, conservation, and restoration. And so this information is key for responsible use of natural resources and regional development, and it's foundational for improving local ecologies and economies. And so an important component of getting environmental data in the coastal environment is through moorings, right? So mooring-based measurements, they're a key component of modern observing systems, but they often can be a little bit more difficult to get, right? So when you're putting something out there in the water, you don't have a hard structure typically to moor to affix things to, and so your mooring systems are, they're good these days, but there's just more inherent risk in mooring things than having a large affixed structure like like a weather station, like a pier you're attaching things to, or a lighthouse, or a oil rig or something of that nature, right? And so these data do give us the data from mooring systems give us very good information, but it can be a little tricky to maintain them in the long term. They can be pretty cost intensive because you have to go out there with boats and service them every so often, right? And so the importance of this data is demonstrated through things like NOAA Buoy Data Center, where NOAA goes around and maintains a number of buoys throughout the United States and in the tropics, probably some other places that I'm not aware of. But the values, is demonstrated through the efforts of the government as well as academic institutions to maintain these sites. And so, to give you a sense of that, this is just the Gulf of Mexico, and here's a couple slides of sort of the western Gulf of Mexico. So the top plot is the western Gulf of Mexico. The lower plot here is the eastern Gulf of Mexico, and then sort of diagonal away from that is sort of the Mississippi Bight. And what I'm trying to convey here is that there's regionally some very large differences in what areas have instrumentation and what areas don't have instrumentation. And I would argue that our little space up here, the Mississippi Bight, is relatively under instrumented compared to the western and eastern Gulf of Mexico. And so this station takes on added importance because we really don't have much in the water in this area. And so this site that I'm going to be talking about, the little buoy that could, it's supported by Dauphin Island Sea Lab and University of South Alabama, or I shouldn't say supported, it's run by University of South Alabama and Dauphin Island Sea Lab. It's about 9 nautical miles offshore. It's basically due south of Katrina Cut. I'm not sure how familiar folks are with the area, but it's about 16 kilometers or 9 nautical miles due south of Katrina Cut. And the buoy's been out there collecting data for over 14 years. This site collects velocity through the water column. It collects near surface and bottom salinity, and it also salinity, temperature, pressure, and it also collects water temperature throughout the water column. Right? And as far as I know, it's the longest running time series of coastal hydrographic data throughout the water column in the Mississippi Bight, and it's probably one of the longest time series of full hydrographic data throughout the water column in the Gulf of Mexico. Maybe Louisiana has some that I'm not aware of. Maybe there might be some others that I'm not aware of, but most time series are of hydrographic conditions are on the surface. There's not many out there that do the full water column. So this site's relatively unique in that sense. So this data, and we'll talk about why that full water column data is important later on in the talk and one of the applications that I'm gonna discuss. Yeah, so this thing is collecting a whole lot of data, and it has been for a very long period of time. So just to give you a sense of what that looked like over the last couple of years. So one of the issues with this site is it's been going for a long time, which is great, but the way in which we funded it has been varied, and that has come from different PIs over the years. Right now, I'm sort of the caretaker of this site, but I haven't been here for the full 14 years that the site's been running, although I am starting to build up quite a few years here. I've been running it for the last 6 years, basically, and so there's a good 8 or 9 years in there that I haven't been in charge, and other people have been in charge, and they've been doing a great job. They've done a great job, but it just leads to differences in how that data is collected, right? So when the site first went out, we had this big hulking icebreaker buoy on it. Over time, well, not just over time, but because of instrument loss or surface expression loss, we've changed the mooring design a bit. So we've moved to a smaller buoy in the sort of middle there. And then currently, a big thank you to the NOAA Restore Science program. They've funded us for this new, more modern buoy. It actually has some instrumentation on it. It's not just sort of a dumb marker buoy. So it's really exciting to have a modern buoy that has instrumentation on it. And so now we get very near surface measurements, sort of consistent with the NOAA buoys that you typically see at the National Buoy Data Center, where we're getting a near surface measurement as opposed to just subsurface measurements. But these sort of iterations just sort of illustrate the changes that this site has experienced over time, right? And so if you look at what the subsurface data collections look like, Well, it's changed, right? So from 2004 to 2009, this configuration, the mooring configuration sort of looked like this first figure. 2010 to 2015, it sort of looked like this configuration, and then the panel to the farthest right there is the modern configuration, where we have actually two lines out there now. We have the historic focal line that has maintained relatively consistent characteristics with the historical data, and then we have our new mooring that's collecting data at the near surface. And actually, we're in the process. It occasionally communicates in real time. We had that going 2 years ago. There were some infrastructure changes due to transitions from 3G to 4G cellular network, and our ability to communicate with the site failed. And so now we're going to Iridium, and we're in the process of getting an Iridium telemetry set up for this site. And so we're hoping to be broadcasting some of this data in real time within the month. So that's kind of exciting to get this site back online and back communicating. But as you can see, these different setups has led to differences in how the data is collected, some of the documentation associated with this data. And so because of all these changes over time and changes with PIs, not all this data is collected, and not all this data has been collected and organized in a way that's conducive to easy use. And so that's why the project was conceived. Oh, before we get there, there's some fun little sidebars here. So, this buoy over the years has done quite a few things, and it doesn't always want to stay on its mooring. So when I first got down here in 2009 as a postdoc, I picked up one of basically the icebreaker buoy. This big thing had drifted off and landed in Miami. So a couple of us drove down to Miami and picked this buoy up and brought it back to Dolphin Island. You can see the middle plot here. This buoy found a way of working itself into someone's backyard. So you can see this bottom plot. This buoy just showed up, and someone happened to be driving around a house in the area and saw our marker buoy in their front yard. And more recently, the surface buoy, which it has instrumentation on it, so it's an expensive piece of equipment. So we actually put a tracker on it. And I don't know if you guys remember 2018, October, we're going to be talking about that quite a bit. But right before Hurricane Michael came through, the buoy broke off its mooring and went on a little journey, and we ended up picking it in 8 days later out of Venice, Louisiana. We hired Cito to run out and grab it, and that's sort of what that picture is up top there. That's the surface expression that was sort of strapped onto a tiny little Cito boat. And they picked it up before this thing sort of ended up in God knows where, getting caught and trained in the loop current. Who knows where this thing would have went. This buoy site does have some adventures in its history, but it keeps chugging away. And so getting back on task here, the motivation, as I mentioned, was to get the inconsistencies in the data processing and the organization straightened out, right? And so these inconsistencies are a significant limitation to dissemination and accessibility of the data to regional stakeholders and the broader scientific community. And so we really wanted to clean up and organize the data set and get it into sort of a compact data package that people could more readily access. And as I mentioned, right, so data from this site is typically collected by instrumentation, and the instrumentation is swapped out every 6 to 8 weeks. And so the goal would be to merge all those 6 to 8 week deployments, right? You can think of 14 years of 6 to 8 week deployments as a pretty large collection of data that has to be sort of worked together, right? Sometimes these depths vary, sometimes you don't have an instrument or an instrument's lost on a deployment. So there's all these sort of hiccups that you have to deal with. The other thing we wanted to sort of get at was cleaner metadata documentation. So because multiple PIs, and if you think back to 2005, metadata wasn't as hot a topic as it is now, a decade ago. And so people's documentation of this mooring site wasn't as consistent as it is now, because the emphasis on metadata just wasn't there back in 2004. And so the goal was to get all the metadata up to standard for what people would expect for a long-term monitoring site. And so organizing the data, providing metadata, and then finally getting this data archived at a place where it will be preserved historically, as well as readily accessible for a range of users. And so a good spot to put this stuff is the National Centers for Environmental Information and CEI. And so the data is also going to be available through www.mymobilebay.com, which technically doesn't exist anymore. It's been sort of rebranded as ARCOS, the Alabama Real-Time Coastal Observing System. So that's the main goal, is to get this organized, correct metadata, and accessible. Mission accomplished. This data so this is sort of the tail end of the project. The project actually, I think, ended this past June 1st. And so technically this project is over. And we did get this data to NCI organized with metadata. And so it is now readily accessible to the general public. And so I've got the sort of the Ascension access, the Ascension number in there, the access link there. It's pretty exciting. So to give you a look at this data, this is sort of a view of the long-term data from the near surface and bottom CTD. This is the temperature profile, and you can see there are gaps in this time series. 2008 is a particularly egregious gap, right? This was when that icebreaker buoy went on its journey and ended up in Miami, and so actually the whole year the data was down. Over the years, we have some years are better than others. Lately, you can see this, since 2014, we've been doing a pretty good job of getting consistent data, although there are some breaks in there. If we look at the salinity, here's the salinity. This sensor is a little bit more, is less robust than temperature, and so there are a few more gaps in this time series, but you can still see some interannual variability here. For those that know the area, 2007 and 2008 were extremely dry, and so you can see that near surface, that red line is pretty close to the blue line relative to some of these other years where things are significantly wetter, particularly in the spring, where we can get salinity, freshwater signals as low as 20 to 25 during the spring. But you can see there's a lot of years of data here. And so if you're thinking about interannual variability, this site's going to give us a window into that interannual variability, both in temperature and in salinity conditions and stratification. So you can start looking at some cool things, right? So if you look at the temperature structure from 2007 versus 2018, if you're just out there measuring 1 year, you might get a sense of things, but having multiple years give us a sense of how things actually change and how things are actually different from year to year, right? And so you can see 2007, there was probably a storm event that mixed the water column. So you can see temperature is in the y-axis, time, so this goes from mid-August to November in both cases, and the lines indicate a temperature time series at that given depth. And so you can see the data is all separated out here, indicating there's strong thermal stratification, and then a mixing event happens, and all the lines converge into a single line. So that means all the temperature measurements throughout the water column are reading about the same temperature. So that tells you it's a fully mixed water column, right? So you go from stratified to fully mixed, and then you can see the temperature loss. As you get into fall, as you'd expect, the temperature decreases over time as you go from early September through October. But fundamentally, this system can be very different, right? So in fall of 2018, you see a very different thing happen, where you see the stratified conditions here in August into September. Then we have a mixing event. This is Tropical Storm Gordon, which you'll be hearing about a lot in the very near future here. It mixed the water column, and then it re-stratified throughout September, and you see the heat content actually goes up. The temperatures start actually increasing in late September. So there's a fundamentally different behavior between the fall of 2000 and the fall of 2007 and the fall of 2018. And so that's this long-term time series gives us that perspective of how different falls can be. And this is just sort of an example of the fall transition, but you can do the same thing for spring or winter or summer. You can look at these seasonal dynamics, right? And so if you look at, to give you a slightly different perspective, not just comparing year to year, if you look at all the years, right? So this is sort of looking at all the falls, doing a depth average value of at each sort of hour of data, right? So we have time, August through November. We have depth average temperature. So that's just taking all the temp data from all the temperature measurements and averaging them over the water column. And what we can see here is the different years are thin lines, and then we have 2018 as the thick red line. And if you look at October, going into October, late September, this 2018 really stands out, right? It's almost a degree warmer than any other year in the past, right? And if you think back what happened in fall of 2018, we had Hurricane Michael, right? And so this, as I'll argue in the next several slides, may have had something to do with why Michael was so strong. So we'll get into that in a minute, but I do think this slide sort of gives you a nice perspective on the benefits of having this long-term time series where you can really see unusual years shake out, and 2018 is a particularly unusual year, which we'll talk about here as we get into a potential application for this data. So that was sort of the lead into some work that I've been doing with some of my collaborators here from Texas A&M Galveston, from JPL out in California, the Jet Propulsion Lab, which is a sort of NASA research center. And so we're going to be focusing on hurricanes and heat waves and how this data, this long-term data that we were able to organize with the funding we got from NOAA, came in handy, basically. And so if we look at the this event, this Hurricane Michael event, right? This was an extreme event that came through, basically pounded the Florida shelf, which we'll talk about in a second. But this case study really highlights how this data set can be used to evaluate extreme events. And so the question is, why do we care about extreme events? Well, extreme events are really important for the resiliency of natural and human systems, right? And so these human systems and natural systems are often tested by extreme events. Big events cause a disproportionately large amount of damage and loss of life, right? So it's not the average events or the small events, it's the big events. It's not linear. You don't just go from big to small in a linear way. There's this nonlinear transition where big events just do way more damage than the smaller events. And so understanding extreme events is really critical for several reasons, right? One, if you couple these extreme events with low frequency trends or low frequency stressors, they can act as a change point. So you can fundamentally shift the dynamics of your ecosystem when you couple a low frequency trend with an extreme push, right? And so you can think of sort of low frequency trend of climate change, global warming, of oceans warming, or of the dissolved oxygen dynamics that we have in the Gulf of Mexico, this hypoxia stressor that we have, the reduction of low DO. If you couple that with an extreme event, you may fundamentally shift your system into a new regime. Extreme events are also really important because they are fundamental to properly evaluating risk and vulnerability of a given region, right? If you don't understand your extreme events, you're not going to properly evaluate risk and vulnerability of a region. So where is this particularly important? Well, places where we have growing human populations, infrastructure, and stressed natural ecosystems. And coastal zones hit all of those sort of key features. So understanding extreme events in coastal zones is particularly important, right? And so as I mentioned, Michael really hammered this area, and it's an example. And so that's what you're seeing here in this image. It's a picture of Panama Beach, or excuse me, Mexico Beach, Florida, where it just got absolutely devastated, right? So this sort of is the lead into what I'm going to be talking about, right? One example of an extreme event that affects a lot of coastal areas is tropical cyclones, right? So these guys are devastating for, or can be devastating for, tropical and temperate latitudes. And so there's good reason to try to understand what causes the intensification of these storms in coastal regions, where they're most likely to impact human infrastructure and people in general, as well as the ecosystems. So and what we're finding is that continental shelves are critical regions for storm intensification, and storm intensification can be very sensitive to the hydrographic conditions in these regions, right? So there's a number of studies that give examples of shelf conditions that can mitigate storms and shelf conditions that can intensify storms. So there's more limited work in these shelf regions, but what we're seeing is that the shelf hydrographic conditions are critically important, right? And this is where our mooring data is going to come in handy. Instead of just having a surface measurement, this mooring that we've been maintaining offshore, we actually have the full water column hydrographic structure. And so that's going to be really handy into evaluating risk and vulnerability to tropical cyclones, because we have that full water column data as opposed to just a surface measurement. Now, where this ties into surface measurements is how the hydrographic shelf conditions represent, or how the shelf hydrographic conditions capture the oceanic thermal properties, and how those thermal properties lead to storm intensification. That information is conveyed through sea surface temperature, right? So this is the key parameter that controls the oceanic contribution to storm intensity, right? So the upper ocean dynamics and the upper ocean thermal structure lead to changes in sea surface temperature. Those changes in sea surface temperature then propagate into storm intensification or storm mitigation, storm attenuation, right? So understanding how sea surface temperature change is directly coupled to the subsurface dynamics. How does that work? Well, we typically see two ways in which tropical storms influence sea surface temperature, right? And that happens through surface fluxes, so surface heat fluxes, and mechanical mixing, right? So that's what I sort of have imaged here. You have the open ocean versus continental shelf. So in the open ocean, in both cases, we're going to have heat loss through surface fluxes. So we have evaporation and we have temperature difference, warm ocean water conveying heat to a colder atmosphere. So that's one way, one sort of component of changes in sea surface temperature. The other component in sea surface temperature is mechanical mixing. So you get big waves, high winds. That's going to take warm upper ocean water, mix it downward. It's going to take bottom ocean water, mix it upwards. And so you're going to get a cooling of the sea surface temperature. And one of the big differences between the open ocean and continental shelf is the accessibility to cold water, right? So in the open ocean, the deep water of the ocean is an infinite cold reservoir, right? No matter how much you mix, there's always going to be more cold water that can be pulled up and brought into the surface layer. And so you can, if you have a big storm and you get big mixing, you're going to get more cold water mixed into the upper ocean, and you're going to get more sea surface temperature cooling. That dynamic changes when you move into the continental shelf, where you have a hard bottom that limits how much access you have to cold water. So even if you have a really big storm and you mix the water column up on the shelf, you can only mix down to the bottom of the continental shelf. You can't mix any further than that. And so that limits your accessibility to cold water. And so that's a potentially important difference between the open ocean and the continental shelf. You only have a limited amount of cold water on the continental shelf, right? So this suggests that sort of open ocean feedback mechanism, that the bigger your storm, the more cold water you're mixing, that's sort of a negative feedback where you could start attenuating your storm as your storm gets stronger and stronger because you're going to be mixing cooler and cooler water into the upper ocean, right? That feedback loop is broken down on the continental shelf, and so this gives a potential for intensification on the shelf that may not be there in the open ocean, right? So the ways in which the ocean, the atmosphere interact to create different hydrographic structures or sort of coastal setups may be critically important to the overall impact of a hurricane as it's making its way into landfall. And so that's what we really want to try to get at with this long-term data that we have at the mooring site, the focal mooring. So the overall goal, right, of this sort of case study is to improve the understanding of compound events, on basically how a sequence of events lead to shelf hydrographic structures that may be favorable for storm intensification, right? And so the hypothesis that we're going to sort of put forth and look at, and again, this may seem a little strange, but the way it's presented now, but you'll see that the sequence of events sort of dictates this be the hypothesis, right? So the idea here is that if we have a strong mixing event, for example, a tropical system that creates mixing, if that's followed by an atmospheric warming period, so say an atmospheric heat wave, this is going to be a sequence of events that creates an oceanic coastal environment that primes the shelf for extreme storm events, right? So you have a mixing event that's going to be pushing heat from the upper ocean to depth, and then you have that followed up by atmospheric warming, which is going to reheat the upper ocean, potentially creating a supercharged thermal environment, right? And so how we can test this and look at this is with data from our mooring, our long-term data from our mooring, and we're going to be focusing on the fall of 2018 because we had this sequence of events come through the area, and so we can see how important this sequence of events actually is. So as I mentioned, right, this is going to be a sort of demonstration of the usefulness of getting all this historical data at site CP, also called focal. I use those terms interchangeably because of the history of the site. The site has a different names, and so I apologize if that's a little bit confusing. I'm just so used to using this data and calling it whatever sort of its name was at the different times of its mooring life that it can be a little bit disorientating to folks. So I apologize, but if you hear me use CP or focal or West End CP, those are all the same names for this long-term monitoring site that we have. So this site, focal or CP, this is going to be the focus of our talk here, where we're going to be zooming in on 2018 and putting 2018 in historical context that we were able to do from this project. The data is now available online. ARCOS is the sort of new name for our observing system, and there's the link that you can click on and check out this site. Hopefully in a month it will be kicking out data in real time, maybe less than that, we will see. But we're going to be using data from this site. We're also going to be using meteorological data from various regional sites, and then we're going to couple that with some satellite data, sea surface temperature and sea surface salinity data. There's a part 2 of this talk that I don't have time to get into that deals with some modeling aspects associated with this work that sort of confirm the observations. But for for the length of time I have, I just wanted to focus in on the observations. So this is sort of the 1D model that we would be talking about in a longer talk, but I don't necessarily want to get into that for today. Although I can take questions about the one-dimensional modeling that we did to confirm that the mechanisms that we're seeing are significant. So getting back to Hurricane Michael, as I mentioned, this was a really intense storm. It was the strongest hurricane on record to make landfall in the Florida Panhandle. It was unusual because of several other reasons. It experienced rapid intensification through landfall. It was the latest date of a landfall Category 5 hurricane to hit the U.S. And interestingly enough, the level of intensification was more than forecasted, right? So what you can see here is a plot of select model forecast from the evolution of Hurricane Michael. So you have time here. This is October 2018. So this is the 7th, 8th, 9th, 10th, etc. The y-axis is intensity. The black line is a observed intensity of Hurricane Michael or Tropical Storm Michael, depending on where it was in its evolution. And the blue lines that are going out, that are originating from those black dots, are model forecasts, right? And so what you can see is typically the black line is well above the blue line, meaning the model forecast that was initiated at a given time step, the forecast prediction tended to underestimate the intensification, which is shown in the black circle. So the blue lines are typically under the black line, which means the forecast was underrepresenting the intensity for the majority of Hurricane Michael's lifespan, right? And so, why is that bad? Well, you can imagine that's going to be bad because people are going to stay at home. They may think the storm's not going to be as strong as actually is, and so they may not evacuate like they should, or they may not board up their property or their business like they should. So that has the potential to cause loss of life and loss of property, or enhanced loss of property. And so this is generally a bad thing. And so what caused this? If you look at the NOAA report, the NOAA report suggests wind shear was probably a factor. But what perked my interest was the fact that this thing intensified through its landfall, right? So it went from a 4 to a 5 as it was crossing the continental shelf. And so that sort of cued to me that, hey, maybe something is going on with the shelf water column. And so if we look at, and I've kind of sort of primed you for this in some of the early slides, if you look at 2018, 2018 really stands out. And again, we can only know it stands out, right? So if we look at 2018, again, the red line is the observed. And so I'll sort of walk you through this plot. It's a little bit busy. We have August through October. Hurricane Michael hit right here. It's that sort of upside down triangle. And then we have several lines and shading, right? So the thin black line is the mean for the long-term time series. So this is a 13-year record. So it's the mean value of that 13-year record. The gray shading is 2 standard deviations away from that mean. And the black dashed line is the maximum observed value, in the time series. And then in the 13-year time record. And then the red line is the observed value in 2018, right? And so what's critically important and why this project was important, because using this project, we were able to organize the data and produce a black line, the mean for the 13-year record, and then as well as the standard deviation, as well as the maximum observed in this 13-year record, right? So all the black and gray shading we were able to produce because we were able to organize and structure this data. And then if we look at what happens in 2018, as I kind of pointed out, this was a extremely warm year in late September, early October, and we see the red line, the observed values in 2018, they overlap with the maximum value observed over this 13-year record, right? So the observed value is the maximum over this 13-year time series during late September, early October, prior to the arrival of Michael, right? So we have this marine heat wave going on. This extreme thermal event is happening in the shelf environment prior to Hurricane Michael making landfall. So this is sort of consistent with intensification as Hurricane Michael made landfall, right? So the natural question for me as a scientist is, hey, what caused this extreme marine heat wave? And then secondly, if we can figure out what caused this extreme marine heat wave, are there cues that forecasters can take home, can use to sort of indicate what might be a precursor to an intense thermal environment that may allow a storm to amplify as it's making on its way towards landfall, right? So are there cues that we can sort of use from this case study to tell a forecaster, hey, if you see this sort of sequence of events, you may have a situation where a storm may amplify before it makes landfall, right? So to me, understanding why this marine heat wave was generated is really important and it may be useful information for forecasters, right? So if we look at what happened in 2018, we really see these two big increases in heat content over the water column, right? We see, so here's our marine heat wave, right, in late September, early October, and then we have our 2 periods of increased thermal activity, right? So you see in late August, this big uptick, and we see another uptick, a sort of broader, slower uptick in mid-September, right? And so what was going on in this first increase? Well, that was coupled with Tropical Storm Gordon, right? And so a lot of things are happening here with Tropical Storm Gordon, but the primary thing to take home for this talk is the mixing that was involved with Tropical Storm Gordon. So if you look at Tropical Storm Gordon, right, so this thing sort of streaked across the area. This is the red line here as it's sort of making landfall. Here's a picture from weather.com. You can see the storm area or the cloud area that's impacted by this tropical cyclone. And what happened here as it trekked across the northern Gulf of Mexico is we got significant mixing happening, right? So if we look at the data, the full water column data we have from our mooring site, you can see before, so this vertical arrow indicates where Tropical Gordon made, or when Tropical Gordon made landfall, Tropical Storm Gordon made landfall. We have time on the x-axis, depth over the water column in the y-axis, and the coloration is temperature. Yellow being warmer temperatures, blue being colder temperatures. And what you can see is when Tropical Storm Gordon approached landfall, we get the upper ocean temperatures mixed downward, that heat gets mixed downward, and the bottom cooler temperatures get mixed upwards. And we now have a water column that has been flushed of its cold water. So there's no more deep reservoir of cold water on the shelf. All that has been mixed upward and combined with that upper ocean heat. And so this is a key component that we basically removed our cold water reservoir from the continental shelf, right? So that's sort of what's going on in that first uptick of heat. The second event is sort of a slower, longer build, right? And so what's going on during that time period? So we have Hurricane Michael here, Tropical Storm Gordon here. That's subsequently followed by this next warming period. Now that next warming period is associated with wait for it, atmospheric heat wave, right? So during this period of time, we see this intense atmospheric warming, right? So again, orientating you, there's air temperature on the y-axis, there's the time is on the x-axis, August to October. The shading is the same as what we saw in the previous slide. The thin black line is the mean over the 32-year air temperature record at Dolphin Island Sea Lab, or excuse me, it's actually the NOAA station next to Dolphin Island Sea Lab. The gray is 2 standard deviations. The black dash line is the maximum observed value. The red is the value observed in 2018. And you can see right when that warming was happening, you see these increasing air temperatures where it's hitting a maximum value sort of right around mid-September, and that there's also this sort of rewarming in late September, early October. So we have this really warm period of time, and what does that do? Well, surprise, surprise, it intensifies the upper ocean heating, right? So we have this intense rewarming of the upper ocean after Tropical Storm Gordon comes through, and so now we have this sort of 1-2 punch where we have the upper ocean thermal warming coupled with a bottom water that has been sort of flushed of its cold characteristics. And that leaves us with a supercharged water column, right? And so we now have this sequence of events that leaves us with extremely warm conditions prior to Hurricane Michael. And so the question you can ask, right, is, well, we're looking at the conditions at a site in the western Mississippi Bight. Michael came ashore in the eastern Mississippi Bight. And so how relevant is what we're seeing in this mooring to what happened to this broader area? And so we can try to tease that out with various lines of evidence. Satellite data is one good way to do that. So here is a plot of the sea surface temperature in the week prior to the landfall of Hurricane Michael. And what's plotted here is sea surface anomalies above 2 standard deviations of the mean. So this is sort of, where is it really, really hot? The red is areas where it's exceeding 2 standard deviations. The blue is where it's below 2 standard deviations. So even the blue is pretty warm. But the red is where the water column's on fire. We have a broad, and what you can see here is there's a lot of bright red here in the northern Gulf of Mexico, and that is consistent with a large area experiencing a marine heat wave during this time period. So the upper ocean warming that we saw at the mooring site is consistent, is happening over a regional scale. If we think about the mixing event that pushed heat downward, we can come up with a way to kind of get at whether or not that was happening over a broader scale. One way we can infer this is through before and after Tropical Storm Gordon went through. So if we look at before and after images of satellite data during and after Tropical Storm Gordon, we can look at how the sea surface and salinity changed before and after, and we can see if that's consistent with mixing, right? So if we look at that satellite data, so maybe getting a little bit ahead of myself, if we look at the 2 storms, so even though the direct tracks may seem very different, if we look at the cloud structure and the area of precipitation impacting the region, we can see Tropical Storm Gordon and Hurricane Michael really do cover the same area. So if we see the cloud coverage here, you can see the broader Mississippi Bight is being impacted in both cases. And so again, as I mentioned, this is going to translate into satellite data. So if we look at satellite data before and after, we can see that differences in sea surface temperature before and after Tropical Storm Gordon, we see there's blue shading here, right? So that tells us that the difference between SST, there's a cooling in the surface of the temperature, the sea surface temperature. And there's also in the other plot here, this is salinity difference from satellite. And there's bright red here, which means the sea surface salinity got saltier. And that's what you'd expect with mixing. If the bottom waters were mixed upward, we'd expect colder, saltier water to be mixed with surface characteristics. And so that's going to cool and add salinity to the upper ocean. And so you'd expect colder, saltier water. And that's in fact what we're seeing. And so this is consistent with what we'd expect at the mooring site. So what we saw at the mooring site likely was happening over the broader Mississippi Bight. One more line of evidence would be comparing the one site that I'm aware of near where Hurricane Michael made landfall, that Panama Beach City fishing pier data compared to our focal mooring data or our site CP mooring data. That's the red and the purple, right? And the gray, the black, thin black, and the dash black are the same as before, the mean, 2 standard deviations, and maximum observed value. But for this plot, what I really want you to see is just the purple and the red lines are overlapping or at least following the same trends for most of the time series here in the run up to Hurricane Michael, which suggests that both sites were behaving in similar ways. And so we have several lines of evidence to say the mechanisms that were operating at site CP/focal/West End CP, all the same spot, were similar to what was happening over the broader shelf, right? So we could summarize what we saw happening through a cartoon, right? Who doesn't like a little cartoon? And so what we've done here is, because we have this long-term time series and we were able to organize it, we were able to identify a new mechanism via compounding processes for generating extreme thermal conditions in this region. And so what did we have here? We had, so A is sort of our event or pre-compound event condition, right? Where we have warm surface water. There's a sharp transition because of the stratification, and we have colder bottom water. B sort of shows where we have this storm come through, mixes the water column, and then we have this homogenized thermal condition. And then the last plot here is the atmospheric heat wave comes through and rewarms the upper ocean. And so the fact that we have heat mixed down during the tropical storm event, coupled with the intense rewarming, leaves us with a supercharged thermal environment, a marine heat wave that is conducive to storm intensification, right? And so, understanding these compound events may help us get better insight to when a tropical storm or a hurricane is approaching landfall. When is it likely to intensify? And when is it likely to get attenuated due to shelf hydrographic conditions? And so with that, I'd just like to acknowledge support for this offshore site through various NOAA agencies or funding agencies, and thank Marine Tech Support at Dolphin Island for helping keeping this mooring going. And so with that, I've sort of had my piece here. I'd love to get some questions or concerns or thoughts from the folks online.
Great, thank you so much, Brian. That was fascinating. Really appreciate it. We are now open for questions. Again, if you have a question, feel free to type it into the chat or Q&A or raise your hand. I do see at least one hand raised. And I also see a comment written in. Tom Johnstone with National Weather Service Tallahassee says it's an excellent presentation. He can't wait to share the recorded version with his staff. So that's a great kudos there. I see a couple hand raised. So
yeah, on that note, there's a talk that's solely dedicated to the second half of this the case study I gave for World Ocean Day, where this talk I only covered half of the sort of full talk because I wanted to go over the long-term time series at this site. So I can send out a link with the sort of full scientific talk that involves the one-dimensional numerical modeling that I didn't have time to get into. That if you're more interested on the science side of this, there's a little bit more detail there. And I should say that this is a manuscript in review right now with Nature Communications, and so I'm working on revisions to that. So hopefully a manuscript based on this work will be coming out in the near future. And so if you want me to send you that, contact me, and as soon as it sort of gets through the peer review process, I'm happy to send that out. Or I mean, if you want a draft version of it, I can send out the draft version with the caveat that it's not through its peer review rigors yet. We've got through the first hurdle where the reviewers have requested a revision and not a rejection. So we're in good shape there, knock on wood.
Wonderful, thank you, Brian. And yes, I see a couple comments saying that it would be helpful if we could get the presentation for World Oceans Day too, the link for that. I'll be sure to send that out in the follow-up, as well as your contact information for further information. I do see a couple hands raised. First one I see, and I apologize, I'm probably not going to pronounce your last name properly. Ebenezer Najiro, I apologize. You're unmuted now.
Yeah, no problem. Hi, Brian. That was a great talk. And we've been looking at Hurricane Michael from satellite products and then also from HICOM model. And I must mention one of the reasons why the models probably are not doing what you expect is maybe the, should I say, the input of salinity. Because in the coastal region, you have a lot of freshwater input, especially in the northern Gulf of Mexico. So that is coming in and that's not being well catered for. So that's one of the things that we saw being problematic with regards to the models. And then you did also mention price paper 2209, where it mentioned that, yeah, it's true, you have to look at the temperature with depth. But that was, if you look at that work, it was done more like in the open ocean. So when you come to the coastal region, especially in the northern Gulf of Mexico, where you have freshwater input, we shouldn't just be looking at temperature, but as you mentioned later on, when you look at salinity, we should be inputting salinity as well. So probably not just looking at heat content, but looking at heat plus salt content, or if you want, maybe density, then that will give a better representation. And that will also help to explain some of the results that you got from the marine heat wave, because that is going to affect the not just the thermospheric effect, but the hydrospheric effect also. And then when you tie that into the heat capacity of the ocean, the freshwater plays a very, very important role. So yeah, those are very interesting results. And I'll be in touch because we're looking at this as well, and we could discuss more.
Yeah, well, it's funny you say that because I'm in the process of submitting a proposal to the NASA Physical Oceanography program to do just that, to focus not just on temperature, but also salinity in the coastal environment. And so, yeah, if you happen to get this proposal to review, hey, it would be great if you said it was awesome.
Yeah, because if you look at the work that you did recently with the JPL folks using SMAP, that gives some very good results on the freshwater plume. And then that also plays a very great role in the hurricanes and how it kills the energy momentum or the heat capacity from the hurricanes. So yeah.
Yeah, I mean, certainly in the open ocean, they're definitely finding out salinity is, plays a big role in influencing intensification, particularly strong storms. And so, yeah, bringing that to the coastal environment, I think is going to be really important.
Yeah, I agree. All right, thank you very much. Great presentation.
Yeah. Awesome, thank you. I also see a hand raised from Juice Sabran. Juice, you're unmuted.
Yeah, I can hear you. Hi, Brian. Good morning.
Hey, Juice, how's it going?
Good. Congratulations on the Nature Communications publication. That's great. Congratulations.
It's not out yet, man. It's not.
Well,
we're not. We're just taking positive steps forward.
Yeah. Well, if it's sent out to review, that's a step forward. That's for sure. All right. Let's see. So I was thinking about your data, and the second time the water column warms up in 2018, that was in September 09, right? And you attributed that second heating event to an atmospheric heat wave, right?
Yes.
But I was thinking that if that warming event went down to what, some 6-7 meters deep, give it or take, so with the surface down to 5 meters, there should have been some mixing anyway, right?
Yeah, so this is a part of the talk I didn't really get to, right? So so the mixing event is sort of, it's more than just mixing heat down, right? So it's breaking down the stratification, right? So by breaking down the stratification in the upper ocean, right, what are you doing? You're creating an environment where the incoming solar radiation can now more easily mix downward into the water column, right? So by removing so after Hurricane Michael comes through, there's really two effects here. I mean, excuse me, Tropical Storm Gordon comes through. There's really two effects. The first effect is you're pushing heat downward and you're clearing your bottom cold water reserve. But the other part of this is that you're making the upper ocean more conducive to heat absorption. And you're doing that because, one, you're reducing the sea surface temperature, so less latent heat and sensible heat are going to be coming out of the ocean. So as you're rewarming, the lower sea surface temperature is going to be reducing the amount of latent and sensible heat leaving the ocean. And you've broken down the stratification, so that upper ocean, that incoming solar radiation, that's typically absorbed in the first meter or two of the ocean. And that, since you don't have stratification there, that's going to more easily mix down to lower depths, right? Because you've broken down the stratification and the water column has to re-stratify, you can more easily mix that incoming solar radiation to deeper depths. And so and then again, that sort of propagates, keeping the sea surface temperature low. So again, as that heat more easily mixed downward, you're maintaining a lower sea surface temperature. And so you're maintaining lower heat fluxes out of the upper ocean. So the upper ocean can heat up faster. So it can respond faster to that atmospheric heat wave because you've broken down the stratification. So there's really there's sort of two elements to that mixing event. It's not only do you push heat downward, but you make the upper ocean more conducive to atmospheric rewarming.
Thank you. That was great. Thank you.
Yeah.
Very interesting. Thank you, Brian. All right. I know we are 3 minutes past the hour. I don't see any further questions in the Q&A, and I only saw those 2 hands raised. So I think we can close it for now. Again, thank you so much, Brian. This was a fascinating presentation. I really appreciate you talking today. And again, I will send out the information and your contact information in the follow-up email to everyone who attended the call. Thank you.
Great, thanks.
Appreciate it. All right. Thank you once again, everyone, for attending. Have a great day.